In this chapter, we will be studying nuclear chemistry. In particular, we're going to take a look at how nuclear chemistry applies to our lives today. So what do we know about nuclear weapons, nuclear power, nuclear medicine, carbon dating, and so forth? Let's start with some basic background information. There's a lot of information on this slide, so I want you to just take a few minutes to follow along with what I'm saying, and then you can pause the video when you're finished and copy down all of the information. If we were to look at the actual mass of particles in an atom of helium, okay, helium contains 2 protons, and each of those protons will have a mass of 1.007276 atomic mass units, which gives us a total mass from the protons of 2.014552. If we continue this process for the other particles, for neutrons and electrons, using those particles' exact mass and the fact that there are 2 of them, we can get a total combined mass for an atom of helium of 4.032979 atomic mass units. However, when we look at the periodic table and we're looking at the actual measured mass of helium, we see that that's not what the real mass is. Mass is actually 4.0026. And if we compare these 2 numbers, we take 4.0330 and we look at the difference when we take away the 4.026, we get a difference of 0.0305. This difference is called the mass defect. It's the difference between the measured mass of an atom and the sum of the masses of its particles. So the sum of the masses is greater than the measured mass, and that is called the mass defect. Now, if you need to, go ahead and pause the video at this point so you can copy down the information. It's not as important that you know all of these numbers, but what is important is that you understand that the mass defect is caused by the difference between the measured mass of the atom versus the combined mass of the particles that make up the atom. Several chapters ago, when we looked at balancing chemical equations, we said that what you have on the reactant side of the reaction has to be equal to what you have on the product side. So if you have certain elements on the reactant side, you will have those same elements on the product side. Okay, we can't just magically get rid of elements. We can't change them into something new. They had to be present on both sides of the reaction. Well, in nuclear reactions, this is not the case because a nuclear reaction affects the nucleus of the atom. Now, we still want the mass to be the same on both sides. Remember, in any reaction, energy or mass is not created or destroyed, it's conserved. So what we're doing is we're conserving our mass. Remember that the number that's written at the top here as a superscript is your mass number. So if we look on the reactant side, we have a mass of 9 from beryllium and a mass of 4 from helium. If we add that up, we get a total mass of 13. On the reactant side, we have a mass of 12 from carbon and a mass of 1 from our neutron. So we also have a mass of 13 on our product side of the reaction. Likewise, we want to conserve our charge. On the reactant side, we have a charge of 4 for beryllium and a charge of 2 for helium, which gives us a total charge of 6. And on the product side, we have a charge of 6 from carbon. And remember, neutrons have no charge. This is the symbol for a neutron. So 6 plus 0 also gives us a total charge of 6. So our reaction is balanced, but what you'll note is that we started with beryllium and helium and we created something new. We created a carbon atom. This is called transmutation. That's the change in the identity of a nucleus due to a change in the number of protons. The number of protons is what identifies the atom. So 4 identifies this atom as being beryllium. The atomic number of 2 identifies the element as being helium. And over here, our atomic number of 6 identifies our element as being carbon. But carbon did not start on the left side of the reaction. We created a new element by combining beryllium and helium. And this is transmutation. We are creating a new element because we've changed the number of protons. This process that occurs where we create a new element because a nucleus is disintegrating is called radioactive decay. It is spontaneous, which means it just happens naturally on its own. And it's accompanied by either the emission of particles like neutrons or electrons, or electromagnetic radiation like gamma radiation, or both. Nuclear radiation in particular occurs when the particles or the electromagnetic radiation is being emitted from the nucleus of an atom during the radioactive decay process. We know that all elements that are beyond atomic number 83 on the periodic table are unstable, and therefore they undergo radioactive decay or nuclear radiation. Let's take a look at the 5 types of radioactive decay. Alpha emission is restricted almost entirely to very heavy nuclei. It's in these nuclei that both the number of neutrons and the number of protons need to be reduced in order to increase the stability of the nucleus. And they do that by emitting an alpha particle, which is going to have a mass of 4 and a positive 2 charge. In essence, it's the nucleus of a helium atom. The way we do this is we look at the element that we're starting with, in this case, polonium-210. When we emit the alpha particle, we're left with lead-206. Remember, when we're balancing radioactive equations, we want to make sure that the mass is equal on both sides of the equation. So we start with a mass of 210 on the reactant side. 4 plus 206 equals 210. We start with a charge of 84 on the reactant side. 2 plus 82 on the product side gives us 84, so our equation is balanced. The next type of radiation is called beta emission. In these types of radiation, the atom is unstable because the neutron to proton ratio is too large. So beta emission is an electron that's emitted from the nucleus, and it's designated by the symbol 0 over -1 with the beta sign. Okay, so remember that if we're ejecting the equivalent of an electron, it's going to have no mass but a -1 charge. Okay, like we did in the first problem, we want to start with carbon-14, and we know that it's going to have beta emission. So what are we going to be left with? Well, we start with a mass of 14 on the reactant side. If we have no mass here with our beta radiation, we're going to be left with a mass of 14. On the reactant side, we started with a charge of 6, and on the product side, we already have a charge of -1. This means that we need to balance that out by having a charge of 7. If we look the atomic number 7 up on the periodic table, we know that that belongs to the element nitrogen. So when carbon-14 goes under radioactive decay, emitting a beta particle, we are left with nitrogen-14. The third type of radioactive decay is positron emission, and this occurs because the atoms are unstable due to their neutron and proton ratio being too small. So they're going to emit a particle that has the same mass as an electron but has a positive charge, and we designate that with the symbol 0 over +1 beta. 0 because electrons have no mass, and +1 because we're told a positron has a positive charge. Just like we did in the previous 2 problems, when we look at our example, we're starting with potassium-38, which has an atomic mass of 38 and an atomic number of 19. When we undergo positron emission, we have a mass of 0 at the top for our mass, so to balance that out, we need to end with a mass of 38. We start with a charge of 19, and because we have a +1 on the product side, we need to end with a mass of 18. 18 plus 1 is going to equal our charge of 19. And when we look 18 up on the periodic table, we see that that element is argon. So when potassium-38 undergoes positron emission, it is going to end up creating an argon-38 atom. The fourth type of radioactive decay is electron capture. Electron capture is also what occurs when the neutron to proton ratio is too small. And remember, our electron has no mass and has a -1 charge. And we're going to use the symbol of a lowercase e for the electron. So this is our symbol for electron capture. Just like in the previous three problems, we need our masses and our charges to total on both sides. So in this case, we have a mass of 106 plus a mass of 0 on the reactant side. To balance that out on the product side, I need a mass of 106. On the reactant side, I have a charge of 47 plus a -1, which is going to give me a total charge of 46. So that's what I need to have on my product side as well. And when I look 46 up on the periodic table, it gives me the symbol palladium. So when silver 106 undergoes electron capture, it will produce palladium 106. The final type of radioactive decay is gamma emission. Gamma rays are high-energy electromagnetic waves that are emitted from a nucleus as it changes from an excited state to a ground state energy level. So the gamma emission usually occurs immediately following some other type of decay, either alpha emission or beta emission, positron emission, or electron capture. And when the other types of decay leave the nucleus in an excited state, as that nucleus goes back to its ground state, it will emit gamma radiation. The symbol that we use for gamma radiation is the Greek letter gamma, and there are no numbers that go with this. So when we use gamma radiation, there will be another type of radiation or emission that is going to be used to balance the equation, but we do have to include the gamma symbol to make the reaction complete. Complete these 4 practice problems showing the product of the radioactive decay of the elements shown. Make sure that you show your notes and these 4 practice problems to Mrs. Benke in class. Please make note of any questions you have so you can ask them in class as well.